Welcome to this coding walkthrough. Today, we will tackle an exciting problem titled Maximum Height by Stacking Cuboids. In this problem, we'll explore how to arrange cuboids in a way that maximizes their stacked height. Let's dive into the details and discover the most effective strategies to solve it. In this problem, we are tasked with determining the maximum height achievable by stacking a given set of cuboids. Each cuboid is represented as a triplet of dimensions: width, length, and height. These dimensions are always positive integers. Now, before stacking, you are allowed to rearrange the dimensions of each cuboid in any order. For example, a cuboid with dimensions width, length, height can be rearranged into length, width, height, or any other permutation of the three values. When stacking cuboids, there are specific rules to follow. A cuboid can only be placed on top of another cuboid if, after rearranging, the dimensions of the lower cuboid are greater than or equal to those of the upper cuboid in every aspect. This means the width, length, and height of the lower cuboid must be at least as large as those of the cuboid placed on top. The goal is to return the maximum possible height of the stacked cuboids under these rules. The output of the problem is a single integer, which represents the maximum height of the stack of cuboids. Let's look at some examples to understand this better. In the first example, we are given three cuboids with dimensions 50, 45, 20, 95, 37, 53, 45, 23, 12. By rearranging the dimensions, we can transform them into 50, 45, 20, 95, 53, 37, and 45, 23, 12. To maximize the stack height, we place the smallest cuboid, 45, 23, 12, on top, followed by 50, 45, 20 in the middle, and 95, 53, 37 at the bottom. This stacking is valid because each lower cuboid has dimensions that are greater than or equal to the dimensions of the cuboid above it. The total height of this stack is 12 plus 20 plus 53, which equals 190. Therefore, the output for this example is 190. In the second example, we have two cuboids with dimensions 38, 25, 45, 76, 35, 3. First, we can rearrange these cuboids as 45, 38, 25, and 76, 35, 3. However, there is no valid way to stack both cuboids because the dimensions of one cuboid are not entirely greater than or equal to those of the other. As a result, we can only use the taller cuboid, 76, 35, 3, as a standalone stack. The height of this single cuboid is 76, so the output is 76. This shows that if no valid stack can be formed with multiple cuboids, the maximum height is determined by the tallest cuboid. In the third example, we have six cuboids with dimensions 7, 11, 17, 7, 17, 11, 11, 7, 17, 11, 17, 7, 17, 7, 11, 17, 11, 7. By rearranging all the cuboids, we can standardize their dimensions to 17, 11, 7. Since all the cuboids now have the same dimensions, they can all be stacked on top of each other. The total height of the stack is calculated as the sum of the heights of all six cuboids. With each cuboid contributing a height of 17, the total height becomes 6 times 17, which equals 102. Therefore, the output is 102. Additionally, the problem includes several constraints and edge cases to consider. For instance, when all cuboids have identical dimensions, they can be stacked to achieve a height equal to the number of cuboids multiplied by their largest dimension. If only one cuboid is provided, the result is simply its largest dimension. Finally, even if no valid stack can be formed, the maximum height is determined by the tallest individual cuboid. To tackle the problem of stacking the cuboids for maximum height, the brute force approach is the most straightforward starting point. The idea here is to try every possible ordering of the cuboids, considering all their orientations, and recursively calculate the height for each valid stacking. For a stacking to be valid, a cuboid can only be placed on another if all three of its dimensions width, length, and height are less than or equal to those of the cuboid below it. Additionally, since cuboids can be rotated, each one has multiple possible orientations where its dimensions can change roles. However, this approach comes with significant limitations. The time complexity grows factorially because we're permuting all the cuboids and considering every orientation, which becomes infeasible for larger inputs. The space complexity also increases due to the recursion and the intermediate states that need to be stored. Ultimately, the brute force method is not viable due to its exponential runtime, making it impractical for real-world use. A more efficient solution is to use dynamic programming, which draws inspiration from the longest increasing subsequence problem. The key insight is to sort the cuboids in a way that ensures a consistent stacking order. First, we pre-process the cuboids by sorting the dimensions of each cuboid so that width is less than or equal to length, which is less than or equal to height. Then, the entire list of cuboids is sorted lexicographically based on these dimensions. This step simplifies the stacking logic. Next, we define a dynamic programming state, where dp, I, represents the maximum stack height achievable with the ith cuboid as the topmost cuboid. To determine dp, I, we compare the current cuboid with all previous cuboids that can support it, ensuring their dimensions satisfy the stacking constraints. If they do, we update dp, I, by adding the height of the current cuboid to the maximum height achieved by the supporting cuboid. Finally, the overall maximum height is simply the largest value in the dp array. The optimized approach has a time complexity of O(n squared), as the sorting step takes O(n log n), and the dynamic programming computation involves O(n squared) comparisons. The space complexity is O(n), as we only need an array to store the maximum heights for each cuboid. One of the key insights here is that sorting the cuboids simplifies the problem by reducing it to a structure similar to the longest increasing subsequence. By pre-sorting the dimensions of each cuboid, we eliminate the need to explicitly handle multiple orientations, which significantly streamlines the logic. This approach was chosen because it is both efficient and intuitive, leveraging well-established techniques from LIS problems to handle the constraints effectively. The balance between time complexity and space usage makes it an ideal choice for this problem, as it avoids the computational pitfalls of the brute force method while remaining easy to implement and understand. Comparing the two approaches highlights why the dynamic programming method is the superior choice. The brute force approach, while conceptually simple, is hindered by its exponential runtime, making it unsuitable for larger inputs. On the other hand, the dynamic programming approach is not only efficient but also scales well with the problem's constraints. It does require pre-processing steps, such as sorting the cuboids and their dimensions, but these steps are computationally manageable and contribute to the simplicity of the overall solution. In conclusion, the dynamic programming method stands out as the most practical and efficient solution. It leverages sorting and well-established techniques to deliver a result that is both optimal and computationally feasible, addressing the limitations of alternative approaches. In this problem, we aim to find the maximum height of a stack of cuboids. Each cuboid can be rotated so that any of its three dimensions can serve as the base or the height. However, a cuboid can only be stacked on top of another if every dimension of the upper cuboid is less than or equal to the corresponding dimension of the cuboid below it. To solve this, we break the algorithm into clear steps. First, we normalize the dimensions of each cuboid so that the length is always greater than or equal to the width, and the width is greater than or equal to the height. This standardization ensures consistency when comparing cuboids for stacking. Next, we sort all the cuboids based on their normalized dimensions in non-decreasing order, first by length, then by width, and finally by height. This helps us establish a valid sequence for stacking. Finally, we use a dynamic programming approach to calculate the maximum possible stack height. Each of these steps builds the foundation for an efficient and systematic solution to the problem. Here, we define dp, I, as the maximum height achievable with the first I cuboids, where the ith cuboid is at the top of the stack. If this condition is satisfied, we update dp, I, by adding the height of cuboid I to the maximum height achievable with cuboid j. Specifically, we set dp, I, to the maximum of its current value or dp, j, plus height, I. Finally, the result is the maximum value in the dp array, as this represents the tallest stack we can build using any combination of the cuboids. Now, we use a dynamic programming approach to determine the maximum stack height. To compute this, for each cuboid I, we check all previous cuboids j to see if they can be placed beneath cuboid I. The condition for stacking is that the dimensions of cuboid j length, width, and height must all be less than or equal to those of cuboid I. This ensures that we account for all valid stacking configurations and always choose the one that maximizes the stack height. Several key insights make this approach both efficient and effective. Normalizing the dimensions of the cuboid simplifies the stacking process by reducing the number of comparisons needed. Sorting the cuboids based on their dimensions ensures that we only consider valid stacking orders, greatly reducing the problem's complexity. The dynamic programming approach optimizes the solution by incrementally building on previously computed results, avoiding redundant calculations. We also need to handle edge cases, such as when there is only one cuboid, or the result is simply the height of that cuboid. Similarly, if all cuboids have identical dimensions, they can stack perfectly, and the result is the sum of their heights. If no valid stacking is possible, the result is just the height of the tallest cuboid. For data structures, we use a list of tuples to store the normalized and sorted dimensions and a 1D array dp to track the maximum heights. In terms of complexity, normalization takes O, n, sorting takes O, n log n, and the dynamic programming step takes O, n squared, resulting in an overall time complexity of O, n squared. The space complexity is O, n, as we only need the dp array. To implement the algorithm, we start by normalizing the dimensions of each cuboid. For every cuboid, we sort its dimensions to ensure the order length equals width equals height. Then, we sort the list of cuboids based on these normalized dimensions. After that, we initialize a dp array where each element represents the maximum stack height ending with the corresponding cuboid. For each cuboid I, the base case is that the stack height is simply the height of that cuboid. We then iterate through all previous cuboids j and check if cuboid j can be stacked below cuboid I. If the dimensions of j are less than or equal to those of I, we update dp I to the maximum of its current value or dp j plus height I. Once we've processed all cuboids, the result is the maximum value in the dp array, which gives the tallest possible stack height. This systematic approach ensures that we account for all valid stacking configurations efficiently and accurately. This Python implementation solves LeetCode problem number 1691, maximum height by stacking cuboids, using a dynamic programming approach. The goal is to maximize the height of a stack of cuboids, where each cuboid can be rotated, and stacking follows specific dimension constraints. Explanation of the code. Step 1. Normalize dimensions. The code begins by sorting the dimensions of each cuboid individually. This ensures that for each cuboid, the smallest dimension represents the length, the middle dimension represents the width, and the largest dimension represents the height. Sorting the individual cuboids simplifies comparison when determining stackability. Step 2. Sort cuboids. Next, the cuboids are sorted lexicographically based on their dimensions, length, width, height. This ordering ensures that we can process cuboids in a sequence where the stacking condition is easier to evaluate. Step 3. Dynamic programming solution. A dynamic programming dp array dp is initialized, where dp I represents the maximum stack height achievable with the ith cuboid at the top of the stack. Initially, dp I is set to the height of the ith cuboid. For each cuboid I, the algorithm iterates through all previous cuboids j, where j less than I, to determine if j can be stacked below I. The stacking condition requires that all dimensions of j are less than or equal to the corresponding dimensions of I. If the condition is satisfied, dp I is updated to the maximum of its current value in the sum of dp j, the maximum height achievable with j at the top, and the height of I. Final step, maximum height. The maximum height of the stack is the maximum value in the dp array, which is computed using Python's max function. Complexity analysis. Time complexity, sorting the cuboids takes O, n log n, and the nested loop to compute the dp array takes O, n squared, where n is the number of cuboids. Thus, the overall complexity is O, n squared. Space complexity, the space usage is O, n, for the dp array. This implementation is both efficient and concise, adhering to the constraints of the problem while ensuring clarity and correctness. Here, we start by normalizing the dimensions of each cuboid. Since the problem allows us to rotate the cuboids, we ensure that for every cuboid, its dimensions are sorted in ascending order. This helps us standardize the orientation, making it easier to compare and stack them later. Next, we sort the cuboids based on their dimensions. The sorting is done lexicographically, first by the smallest dimension, then the middle, and finally the largest. This ensures that when we analyze the stacking possibilities, the cuboids are already arranged in a way that respects the stacking rules. After sorting, we initialize a dynamic programming array, dp, where each element represents the maximum height achievable with the cuboid at that position as the topmost cuboid. We also maintain a variable, maxHeight, to track the overall maximum height across all configurations. The dynamic programming loop begins by setting dp, I, to the height of the current cuboid, as a single cuboid on its own contributes at least its height. Then, for each cuboid at position I, we check all previous cuboids to determine if they can be stacked underneath it. To check if one cuboid can be stacked on another, we ensure that all three dimensions of the lower cuboid are less than or equal to the corresponding dimensions of the upper cuboid. If this condition is satisfied, it means the lower cuboid can support the upper one. In this case, we update dp, I, to the maximum of its current value or the sum of the height of the current cuboid and the maximum height achievable with the lower cuboid. This ensures we are always keeping track of the best possible stacking configuration for each cuboid. After processing all previous cuboids for a given position, we update the global maxHeight to reflect the highest value in the dp array so far. Once all cuboids have been evaluated, the maxHeight variable will contain the maximum height achievable by stacking the given cuboids. Finally, we return this value as the result. To solve this problem, we first need to normalize the dimensions of each cuboid. Normalization means sorting the dimensions of each cuboid in non-decreasing order. For example, the cuboid with dimensions 4, 2, 3 becomes 2, 3, 4, while 1, 2, 3, and 4, 4, 5 remain unchanged since they are already sorted. After normalization, the cuboids are represented as 2, 3, 4, 1, 2, 3, 4, 4, 5. Next, we sort these normalized cuboids lexicographically. This ensures that smaller cuboids, which are more likely to fit below others, are considered first. After sorting, the order becomes 1, 2, 3, 2, 3, 4, 4, 4, 5. Finally, we initialize a dynamic programming array, dp, where dp, I, represents the maximum height achievable with the ith cuboid at the top of the stack. Initially, each cuboid's height is just its own height, so dp equals 3, 4, 5, corresponding to the heights of the sorted cuboids. Now, we proceed to check stacking conditions to determine if a smaller cuboid can be placed below a larger one. For each pair of cuboids, j, I, we check if all dimensions of cuboids, j, are less than or equal to the corresponding dimensions of cuboids, I. If stacking is possible, we update dp, I, to reflect the maximum height achievable by stacking cuboids, j, below cuboids, I. For example, when I equals 1 and j equals 0, the cuboid 1, 2, 3 can be stacked below 2, 3, 4, so we update dp, 1 equals max, 4, 3 plus 4 equals 7. Similarly, for I equals 2 and j equals 0, 1, 2, 3 can be stacked below 4, 4, 5, and dp, 2 becomes max, 5, 3 plus 5 equals 8. Further, for I equals 2 and j equals 1, 2, 3, 4 can also be stacked below 4, 4, 5, so we update dp, 2 equals max, 8, 7 plus 5 equals 12. After these updates, the dp array becomes 3, 7, 12, representing the maximum height achievable with each cuboid at the top of the stack. In this example, the input consists of cuboids with dimensions 1, 1, 1, 2, 2, 2, 3, 3, 3. Since each cuboid already has its dimensions in non-decreasing order, normalization does not alter the input. The cuboids are also already sorted lexicographically, so the order remains 1, 1, 1, 2, 2, 2, 3, 3, 3. We initialize the dynamic programming array, dp, to the heights of the cuboids, dp equals 1, 2, 3. Then, we check stacking conditions. For I equals 1 and j equals 0, 1, 1, 1 can be stacked below 2, 2, 2, so dp, 1 equals max, 2, 1 plus 2 equals 3. For I equals 2 and j equals 0, 1, 1, 1 can be stacked below 3, 3, 3, leading to dp, 2 equals max, 3, 1 plus 3 equals 4. Lastly, for I equals 2 and j equals 1, 2, 2, 2 can be stacked below 3, 3, 3, so dp, 2 equals max, 4, 3 plus 3 equals 6. The final DP array is 1, 3, 6, representing the maximum heights for each stacking configuration. After checking all stacking conditions, the maximum height that can be achieved in this edge case is simply the largest value in the DP array. Since DP equals 1, 3, 6, the maximum height is 6. Now, let's consider a different scenario where the cuboids are non-stackable. For the input 4, 4, 4, 3, 3, 3, 2, 2, 2, we first normalize the dimensions, but since all cuboids already have dimensions in non-decreasing order, normalization does not change their values. Next, we sort the cuboids lexicographically, resulting in 2, 2, 2, 3, 3, 3, 4, 4, 4. We initialize DP to the heights of the cuboids, DP equals 2, 3, 4. In this case, no cuboid can be stacked on top of another because the dimensions of each cuboid are strictly smaller than the one below it. Hence, no updates are made to the DP array, and it remains 2, 3, 4. Finally, for the non-stackable cuboids, the maximum height is determined by simply taking the largest value in the DP array. Since DP equals 2, 3, 4, the maximum height is 4. This example underscores the importance of the stacking conditions, as it demonstrates that not all configurations allow for stacking. By systematically normalizing dimensions, sorting cuboids, and applying dynamic programming to maximize the achievable height, we can solve the problem effectively for any input. To analyze the time complexity of our solution, we start with the normalization of dimensions. Here, each cuboid's dimensions are sorted in ascending order. Since each cuboid has exactly 3 dimensions, sorting one cuboid takes constant time, O(1). For a total of n cuboids, this step requires O(n) time. Next, we sort the list of cuboids lexicographically based on their dimensions. Comparing 2 cuboids during sorting also takes constant time, O(1), because each comparison involves only 3 values. Sorting the entire list of n cuboids, therefore, takes O(n*log) n time using an efficient sorting algorithm. Finally, we apply a dynamic programming approach to compute the maximum stack height. Using a nested loop, the outer loop runs n times, and for each iteration, the inner loop considers all previous cuboids, leading to a total of n*(n1/2 comparisons. This results in a time complexity of O(n²) for the dynamic programming step. When we combine these steps, the normalization step contributes O(n), sorting the cuboids takes O(n*log n), and the dynamic programming computation requires O(n²). Since O(n²) dominates the other 2 components, the overall time complexity of the solution is O(n²). Now let's consider the space complexity. First, the input list of n cuboids uses O(n) space, as each cuboid is represented by a list of 3 integers. Additionally, we maintain a dynamic programming array of size n to store the maximum stack height at each position, which also requires O(n) space. Finally, the sorting algorithm may use auxiliary space, such as temporary buffers, which in the worst case can require O(n) additional space. Thus, the total space complexity of our solution is determined by these components. Adding the contributions from input storage, the dynamic programming array, and sorting overhead, the overall space complexity is O(n). To better understand the efficiency of this approach, let's compare it with a naive solution. A brute force method would involve generating all possible subsets of cuboids, followed by testing all permutations within each subset to find valid stacking orders. This approach has a time complexity of O(2 to the power of n*n), which grows exponentially and becomes infeasible for larger values of n. In contrast, our optimized solution uses dynamic programming to reduce the problem to sorting and efficient pairwise comparisons, achieving a time complexity of O(n²). This is a substantial improvement, making the solution practical for much larger inputs. Now let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, where no cuboids can be stacked because their dimensions do not align, the dynamic programming computation still iterates through all pairs of cuboids, resulting in a time complexity of O(n²). In the average case, for randomly distributed cuboid dimensions, the LIS-like computation also requires O(n² comparisons. Even in the worst-case scenario, where every cuboid can be stacked, the algorithm performs the maximum number of comparisons, but the time complexity remains O(n², as it does not exceed this bound. Mathematically, the nested loop in the dynamic programming step runs for a total of n*(n1/2 iterations, simplifying to O(n squared). For space complexity, the dominant factor is the dynamic programming array, which uses O(n) space. Sorting overhead and input storage do not increase the asymptotic complexity, so the total space usage is limited to O(n). When solving this problem, there are several common mistakes to avoid. First, it's important to always sort the dimensions of each cuboid, such as width, depth, and height, in a consistent order. If you don't, the stacking validations might fail because the orientations won't match correctly. Next, make sure to account for all possible permutations of cuboid orientations. Each cuboid can be rotated in different ways, and ignoring these possibilities can lead to suboptimal stacking arrangements. Another common pitfall is assuming that the input is already sorted or valid for stacking. In reality, you need to pre-process the input to ensure all conditions, such as width being less than or equal to depth and depth less than or equal to height, are satisfied. Finally, avoid using inefficient recursion without memoization. Recursively exploring all combinations without caching results will lead to redundant calculations and exponential runtime. Instead, rely on dynamic programming with memoization to optimize performance. Another mistake to watch out for is misunderstanding the base cases in dynamic programming. For example, failing to handle edge cases, like a single cuboid or an empty input, can result in runtime errors or incorrect outputs. Always take the time to validate these scenarios in your solution. Now, in interviews, it's helpful to recognize this problem as a variation of the longest increasing subsequence problem, where the goal is to maximize height instead of finding the longest sequence. Identifying this pattern allows you to apply LIS techniques effectively. Interviewers also expect you to propose a dynamic programming solution with O(n)² complexity. Be ready to explain your transition function in detail and describe how you pre-process cuboids by sorting them and considering their orientations. Additionally, be prepared to discuss trade-offs between brute force, recursion with memoization, and bottom-up dynamic programming. Highlight how pre-processing and sorting reduce redundant calculations to make your solution more efficient. It's valuable to see how this problem relates to other problems on LeetCode. For example, LeetCode 354, Russian doll envelopes, is conceptually similar, focusing on nesting envelopes based on their dimensions. Another related problem is LeetCode 300, the longest increasing subsequence, which forms the core logic behind stacking cuboids. Of course, LeetCode 1691 is the specific problem we're tackling here, where the focus is on maximizing stack height. Lastly, LeetCode 368, largest divisible subset, is another problem that involves sorting and memoization techniques, showing how these principles apply across a variety of subset-based problems. Exploring these related problems can deepen your understanding of the techniques involved and improve your ability to identify similar patterns in different contexts. There are also alternative approaches to solving the problem, each with its own trade-offs. A brute force approach would explore all possible permutations of cuboid orderings and orientations. While this method is simple to implement, it's highly inefficient, with a factorial time complexity that makes it impractical for large inputs. A more effective solution uses bottom-up dynamic programming. Here, you sort the cuboids, treat each as a potential base, and calculate the maximum height achievable by stacking valid cuboids on top. This approach is much more efficient, with a time complexity of O(n)², but requires careful attention to sorting and transition conditions. Lastly, a greedy approach combined with LIS optimization can also be used. This method focuses on pre-processing the cuboids and applying the longest increasing subsequence algorithm to maximize the stack height. While it can be faster in some cases, it's less intuitive and requires additional pre-processing. Understanding these approaches helps you choose the most appropriate one based on the problem constraints and input size. Thank you for following along. Today we learned how to solve the maximum height by stacking cuboids problem using an optimized approach. We hope the key takeaways and techniques shared will help you in future coding challenges. Don't forget to practice, and we'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!